So, back to some happier, I don't know whether it's happy or not. So, the course materials. So, last time we talked about some, actually, it's long time ago we talked about CNN, I guess. And you guys have lots of great presentations out there. I didn't have time to really go for all of them yet, so I'm pretty much backlogged. And, for the we talk about CNM and also some architectures. So we try to okay, this time we're trying to visualize CNN, like in the sense like if you remember, we said that okay, you can look into the weight. Okay, maybe I just go directly here. We can look into the weight, like, but it's only useful like for the first level there. So you can check out the weights there, and you can, it's kind of immediately interpretable. Oh, of course, like when I talk about CNN for these guys, we're looking into like a vision problem. So you have like either object recognition or like detection and so on. And so if you look at the first level here, and then you look at the weight and plot it out, so you basically will get stuff like this. But if you go to higher level, you can still plot it. If you remember, there's a demo by Kapafi, like I think it's like a Complet.js demo. That one, they plot out all the weights there, but for high levels, basically you cannot interpret that. It's kind of meaningless. So what can we do? Okay, before that, like, I like to kind of like give a remark that like if you are aware of some image processing, or you have some experience of image processing, if you look at pattern like that, it's very much like the Gabor filter, like in image processing. People at the beginning think that it's quite interesting, but they immediately realize no matter what kind of data you put into to train it, the first level always get you something like that. So it turns out it's something pretty lateral. It's not just restricted to neural network, but also other machine learning models. So some other words for visualizing the complet, the kind of like more early work like is by Siller and Vegas. So in the work there, basically they propose two different approaches to visualize this kind of the convolution network, like kind of to understand what's going on inside the network. So the first approach basically is, think of like I have a object recognition problem here. So I have some pictures here. Let's say this is recognized as a Pomeranian. That's kind of a dog of this type that I don't know. Like I don't actually know that kind of. Yeah. Anyway, that is a Pomeranian, I guess. And this is like recognized as a car view, and so on. So, and what they did is basically they're trying to have this image and occlude part of the image and see what's going on of the output score. So, of course, you expect that like, if I occlude some parts here and there, then I will affect the score, right? Or something like, actually, what do you expect if I occlude here as shown here, this dot here? Do you expect the score is higher or lower to recognize this Pomeranian? Actually, the score will be higher. Actually, you can think of this image also. This image, it can't recognize this Afghan Han, I guess is how to pronounce that, maybe. And if you, let's say if you have this occlude this person head here, the head of this guy here, do you expect the score is going to go up or down? Yes, it actually go up. Of course, like if you're going to occlude this dog face here, then this score will go down. Actually, will go way down. So the result is quite intuitive, like kind of expected. Like for example, for this image, if you occlude white at the middle, like occlude the head of this dog here, then the score like go way down. So basically, blue color correspond to like getting a lower score, and then the red color is going higher score. So if you occlude anything else, the score will go up. So it's getting less confusing, basically, this image. And also this one here, if you occlude those people head, like you will have score going way up, because it's less confusing for the model to realize, okay, you're interested in the dog rather than like something else. And this is like the experiment. It's kind of interesting. So another more direct approach is trying to instead of looking into those values directly, as I mentioned, is basically we cannot do that. So what we can do is, let's say in the last layer, you have all the classes, right? For example, this is like a lateral chain to recognize different objects, like for classification. Then for the last layer, immediately before the classifier, should have lots of information, kind of high-level information about the image, right? So you can imagine like this will correspond to something like, if you just look at this vector, hopefully something close to a dog, like if two vectors is close together, very similar, then they are both referring to a dog class. Or like if like I have another one, the cat may be close to the dog, but it's kind of farther away from a rat, or maybe, I don't know. So then, okay, someone tried that. Basically, that's the Hinton group. They try to use the Teasley visualization. Teasley is like some kind of like clustering approach. It's kind of like PCA. So, but in terms of visualization, it's typically much better like than PCA. So I like to go. Actually, this is a slide I prepared. I'm not sure you're interested in, but a little bit side note about Teasley, because Teasley actually is a very widely used method for visualization. Basically, it's an improvement of another used to be a very popular approach called SLE. So it's a stochastic labeling embedding. So the idea is very simple. Basically, you have points in the original space, right? And then you look at the distance between points, and then you look at the distribution profile. So you're originally in a very high dimensional space, right? It's like PCA, you want to reduce into a low dimensional space. In this case, you reduce to just a 2D case, because you use that for visualization, right? Typically reduce to 2D space. So then what your target is, basically, you have the distribution of all the distance between points, and you have the original distribution from the high dimensional space, and you want to match it with, or like the other way around, you want to match the distribution of the distance in the low dimensional space with the original distribution in the high dimensional space. So now let's say xi is the points in the high dimensional space and yi is the reduced space. Then basically the distribution they use is just a Gaussian distribution, the original SLE. Then the whole idea is very simple. Then what they did is just trying to minimize over the KL divergence that actually we kind of mentioned earlier. Maybe you forget about it, but the equation is pretty simple. If you have two distribution, P and Q, then the KL divergence is just sum of P log P over Q, and sum over all the basically over all the variable in the space, all the possible outcome. Then actually one thing interesting to point out is that like this is KL divergence itself. Know that it's very much like a distance measure. You measure like the distance between two distributions, but this distance is not symmetric. So if we talk about, apparently you look at this definition, the KL divergence between P and Q will be different from the KL divergence between Q and P, right? I will have like Q log Q over P instead. That will be totally different. But this setup is more reasonable than the other way around, because if I set it this way, then basically if you think of in the high dimensional space, when two things are far apart, then this P, because you have this Gaussian-like distribution, right? If 2 points are far apart, then this value will be small, right? So this value, it will be small, then I don't care what this value is, still the cost will be small. This term will be small. But on the other way around, if these 2 points are close to each other, so in the high dimensional space, if 2 points are close to each other, then I want those points to be in the low dimensional space to be close to each other as well. So yes, it is reasonable because if you put it in the other way around, okay, anyway, I will give you an example, maybe it will make more sense. So anyway, this is the SLE, and TSLE is basically just trying to solve one of these issues known as the crowding problem. Basically, you have, if you use SLE to generate a visualization point, many times what you get is like you have this one of these clusters just all kind of concentrate into just one point, like just shrink into just one point. So it doesn't help a lot, like in terms of visualization. So they basically solve this problem simply. Again, like this is one of these really beautiful paper in the sense that they have one of this very tiny trick of this original approach and make so much impact in the work there. So this basically what they did, as I mentioned, like instead of like for this low dimensional space, instead of using the Gaussian distribution, they use a T distribution. So the property of T distribution is that So I guess some guys come up. I guess you need to turn on the TV. So basically the T distribution, the main you probably don't need to know the detail of this map here, but one thing you should know is that the difference between T distribution from the Gaussian distribution is that it has a heavy tail. So for this one, what I mean by heavy tail is that like Gaussian is more or less, maybe this is 0 here. So Gaussian maybe I draw it again. Gaussian may be more or less like this. So it's kind of decay very quickly as it go far away. And for student T distribution, you have a kind of heavy tail. It's like the peak is not as sharp, but then like you have a very big tail like on the side. So using the student T distribution, like solve one issue like this. If you have like high dimensional space, let's say if I have just 2-dimensional space, as a very simple example, and kind of reduce to like 1-dimensional space. So let's say you have 3 points here. Let's say I have 3 points here like this. Then I want to maintain the distance distribution, right? So I have these 2 points are close to each other. These 2 points are close to each other. Then I probably will have like, let's say this is A, B, C, 3 points like that. Then we'll have point B here. If I project it to 1D, it would be like that, right? I have A here, and I have C here, right? Yes. Can you see that? Okay, I kind of can see my slides. Yes. Did we mute that? Oh, okay. That maybe like, yeah, maybe we okay. Let's see.
Yeah.
Can you hear us?
Yeah.
Oh, okay. Thank you. So Oh yes. Yeah, the trick I have is I ask for some these social network guys like along the door. I think it's not social network. The education people, they always have keys, and or like Dr. Hassan Rifai, he has key also if he is in the office. Yeah, I don't know. I called IT this morning. They didn't fix the one for 3108, and that's so sad. I mean, like it's since last Tuesday now. I don't know. Yeah, maybe in the evaluation, like you guys can mention like IT is not helping. Yeah. Oh, yeah, anyway. So, okay, from here, like 2D to 1D. So, what you can see, okay, I guess I have a little bit echo. Yes. Oh, actually, Tosa, I guess it's better you mute it. Then it won't echo back.
I am not able to do that. Risk engagement from responding.
Yeah, then that's fine. Maybe I try to lower the maybe I can lower the volume or something like that. Let's see if I can do that. Let's do. No, I guess. Sorry, I need to get. Okay, I Leah, maybe Leah. Okay, let's see. Okay, maybe I did it. I'm not sure. So yeah. Okay, we try this also, but it looks like it's not echoing anymore. So so then you look at this. Okay, you want to maintain distance distribution, right? So you have A, B, B, C is fine, but then you look at A, C here, they are close to each other also, right? But here you are forced to have like a much farther distance. So you want to maintain to have the same probability, then you need to make sure that this distribution in the lower dimension to be more linear about like things can stretch farther apart. So therefore you need a heavy tail there. So then like once you use a heavy tail distribution, then you fix lots of these issues, and then like you have like very nice visualization like what we have here earlier, and then like in terms of actual implementation, you're trying to just do a optimization over the cost function, again just kind of steepest descent, that kind of stuff. Then if you compute the gradient there, what's interesting that you can interpret this as like more or less like with each of the point in the low dimensional space correspond to all the points there, like correspond to current yi and yj. And it just outlines that like for a particular point here, yi, I have essentially some force like applying to this yi, kind of like some kind of tension to kind of pull or push these points like to each of this direction. And the force is like you can derive like to be like this. But this is very much like a real physical model. You're doing some simulation, and you have the force is just or like equal to this computed as here. But what's interesting, because like it's like so therefore like for each step trying to get to the optimum, you just have to each point you go for each of the point and compute all the force, and then try to push the point like in different directions. So as you imagine, like if you have like a large data set, for example, like let's say more than 10K data points, then this naive implementation will be pretty slow. So one easy fix for this is to think of like if you have a couple points here and there. So, and if you have points that are far away, let's say I have one point here, and I have a couple points that are far away, and also like in the same direction away, then actually you can combine the force there. So you can just, for these points, you just like approximate this force by a force applied from the central of, what do you call that? Like central. Oh, basically the center of this point here, right? Center of gravity I'm looking for. Yeah. Then these three forces can be combined into one single force, like maybe like this, right? So that this will speed up the computation, and this actually has a name for that. It's known as the Barnes-Hart approximation. Interestingly, actually originally from the actual physics. And you can further speed things up if you look into quadtree structure, but I won't go into detail for that. Basically, if you first partition those yi into a quadtree structure, then it allows you to quickly to determine if a point cloud is actually sufficiently far away, and also you can easily quickly pull out the center of mass for all those point clouds. And that's one paper actually is kind of published, not exactly published. There's a online journal. You can look for this paper, just Google it. But it's interesting also. Like this is like published in a kind of a I would say a very non-typical journal known as Distill. It's like kind of trying to the journal is try as the name suggests, trying to distill ideas. So it's trying to translate some idea from papers into something easy to understand. So, but there are not many articles there. Basically, I don't think like people like to publish that because lots of work and I'm not sure I should say about that. But anyway, but yeah, that's actually a fun paper to read because it's actually published online as a website. So therefore, you can play with that. You have some simulation there. You can it's not just like reading it. You can play with it. And that's the visualization. You can that I'm not sure. I have internet here. So if you follow this link here, you'll get to a really big visualization result of the ImageNet created by Karpathy. So basically, each of these tiny images basically each of these tiny pixels are images. So of the same class. So what you can see is, you cannot see here apparently, but if you go to that website there, for example, in this region you have some bird there, you have different kind of birds like here and there, and then you maybe next to that you have some mammal, or then you have cats and dogs close to each other and so on. So, and this is using Tisley to visualize that. So we can go even lower, kind of like a finer. Okay, Tisley only look at more or less the last layer, right? Also, of course, you can also look at the other layers, but I don't think many people do that. Like so, but other way to do that is using kind of convolutional approach, or the convolutional approach. So it's very much like backpop. The idea is very simple. Basically, let's see if I can find a lateral here. Let's say I have a lateral here. So let's say I have an image going into the lateral. Then after I going through this lateral, for each of the layer, I have some weight here, right? So I want to see what's this weight actually represent. Then one way I can do is I will remove. Let's say I just want to interest in one particular weight. I want to see what this weight actually represent. So one way I can do is I would just for all the weights in the lateral, I would just set to 0. Everything I set to 0. But just for this weight, I try to backpop that information to the original image. So basically just doing back propagation. Then of course it will generate some image here. But the problem is if you just do that, the image will be very messy. It's like this one. You cannot see much. So there's some several ways to several improvement have been proposed in the last several years. One way is so-called Decomp Approach. So instead of doing a regular backpop, it do a kind of a so-called, they call it a deconvolution. I will go more detail into that. Another way is to doing so-called guided backpop. So we will look into both of those. So the Decomp Approach, as I mentioned, the Silla and Vegas paper. Actually, in that paper, besides they talk about this occlusion experiment, they also talk about this Decomp Approach. So essentially, it's very much like a backpop, but instead of pure backpop, it's just why I think why they call it deconf, because it's very much like you have the in the after you're going all the way in the later layers, you just going backward, very much like going through a forward convolution. So for example, when you do when you go through the convolution network, you may have some activation layer. For example, you have a value there. When you're going backward, in a typical backpop, it shouldn't be a value anymore. Right? So actually, more precisely, do you remember what? Do you think? Actually, maybe I'll ask you later on when I have a figure. So, but actually maybe I can even go to that. So that's regular backpop, right? If you think of that, if I go for a value layer here, so for example, these are the coefficient there. When I go for a value, what's going on is like everything is negative with set to 0, right? So when I do backpop, so what was, for example, this is the gradient. When I go backpop, what's going on is during the forward layer, during your forward propagation, only when the value are positive, then the value is kind of turned on, right? So in that region, right? In this region, then the gradient is basically just 1, right? So therefore, when the input is bigger than 0, so therefore, like, you should essentially just backpop the original gradient to the upper layer, right? So therefore, like for this guy here, so these 5 values here are bigger than 0, right? So therefore, like the values here, here will be just backpop back to the earlier layer. And for the rest of this coefficient there, so because when they are less than 0, then this is essentially the value layer just basically stop the propagation, right? And therefore, like the gradient there should be equal to 0, right? So therefore, in those places should be just 0. So that's the original backpop, right? So now for the decomp, what they did is they essentially just do backpop. Not backpop. For the backpop step here, they just essentially go for a same value layer here. So therefore, like everything is positive, it will just keep it to be the same value. So everything is negative is just equal to 0. So as you can see, like it actually, if you think of that, it doesn't make much sense. So, but it turns out it just worked. So, so that's what they did basically. Like when they trying to pass through this information from the later layer back to the original image, they just map value back to value. And then like when they have unpooling, so basically, I don't know, I have an example here. So remember that if you have a pooling, then let's see. So okay, I don't have, okay, maybe I just draw it here. So when you have a pooling, for example, if you have mass pooling, so originally you have after mass pooling, like maybe like 2 by 2 mass pooling get 1 coefficient here, right? So maybe originally 3, 1, 2, 1, let's say. So after mass pooling, I have 3 here, right? So that's the maximum among these 4 coefficients. So when I backpop back this information, so I now have some gradient, let's say I have some values, it's like 2, let's say. So what I'm going to do is I'll only pass this information to the location that originally contribute to the information here. So therefore, I will just have this set to 2, and for the other coefficients there, I will just set to 0. And that's called an unpooling step. That's what they did. And actually typical what people did also. And then like in terms of filters, like that would just replaced by a transpose of that filter. And this is the decomp flat. And if you do that, like the visualization is pretty good, basically very nice. So this is for layer 2. You're going back, like you can see like okay, layer 1, as we showed earlier, is like you can just look into just the weight, right? You can visualize that just looking at the weight. All of those are kind of like the Global filters. But if you look into a higher layer, like layer 2, you have some more complicated features there. If you go even higher, then you have like really complicated features. Like layer 3, you can, like for example, they recognize wheel here. I'm not sure you can see the wheel there. Here like for example, this kind of recognize face. Maybe this is not high level enough. Let's see. This is level 5. trying to recognize dock, you can see like it's kind of only activate from the dock phase, right? So that's what you expect also. And this, any question? Basically, this is the Decomp approach, and the guided backpop is basically very much similar to backpop, almost like identical to backpop. The only thing is that it combined with the Decomp approach in the sense that when you have this going backward for a value layer, you will kind of like combine both like backpop, that like whenever your original value is positive, you fill in the gradient, but also only when like the gradient are bigger than 0, you will fill in non-zero. Okay, I guess I didn't articulate it very well at all. So basically, when you have gradient like this, everything will be set to 0, kind of, almost. You will pass that non-zero only when the gradient here is bigger than 0, and at the same time, the original input there is bigger than 0. So they call it guided backpop. It turns out it gives like very nice visualization as well. So yeah, something like this is using guided backpop. I don't know which layer is that. So you can see like docs here, I'm not sure which layer is that basically. Oh, okay. This is like Comp 6 and Comp 9 layers. So this is like a deeper layer. So you can really see the dock there. Basically, you can't recognize the dock. So for the body here, it's not very important. You only see the dock head here, and also like this dock, more or less you only see the dock head there. And also like apparently this is cast for faces. I guess like the shoulders are not very important. You just mostly only see the head there, see the head here. So there's some interesting, I'm not sure it's an interesting application, but at least someone tried to use that. Okay, one thing you can imagine, say what you can use is, it looks like you can use this to kind of do segmentation, right? For example, like I can use, or like object detection. So I have an image that I'm trying to recognize, and at the same time I try to figure out where is this object there. For example, like I expect there's actually I don't even know whether there's a face there or a dog there, but anyway, I can go into the the deeper layer and just trying to do a guided backpop. When I'm going back, I will have the most interesting object back, right, in that location. Right? So therefore, I can use that to kind of localize where is the object of interest, kind of. And people use this idea for segmentation. So basically, like they use that to generate so-called salient map. So they think of, okay, this you give an image, then you go through the neural network, you go for a deeper layer, and you go for either guided backpop or decomp. Then you have a mask there, right? And the mask there will correspond to the parts that most likely have the object of interest. So therefore, we say that's salient for that part. And then for that salient part, I can further do the segmentation, right? We can use some classic segmentation approach, for example, grab cut. Then you have something pretty nice, but I think it fails sometimes. You don't, but at least it's some interesting work. So what I'm doing with time actually. So oh, okay, what's this slide is about? I can't forget. Oh yes, this is another experiment trying to see like if you trying to see like, okay, which region or which region in the image will come maximally like activate the new ones. Okay, but I won't go into much detail for this one, honestly. Instead, I will talk about another way to kind of do visualization. The way we mentioned is like we go for like Disney and we first talk about, I forgot already. So anyway, and then the one we just talked about is like using backpop, right? So another way to do it is like to trying to do it through optimization. So for basically like you can use optimization like for two ways. One way is like you have some image and you want to see like whether this how much information is captured in the neural network model. So for example, like if I have some image coming in, so and then like I have a neural network model like somewhere, right? So this is like some particular layer, let's say, and I create a cost function that basically like this is basically the output of the this is the output of the neural network, let's say. Some layer, let's say some fixed layer, or like you can use the entire network even, but let's say just some layer. And then like you just put in some arbitrary input and try to generate something that is close to this one, right? So and this is a loss function trying to measure the difference between the arbitrary input x with the one fixed with the original image, the ground truth basically. And then we want to, but just this alone is not sufficient, because if you just try to optimize without this regularization, basically almost always we just get some garbage, because like if you think of that, lateral images are very unique, because like think of like you have a random function, right? Your images are just a 2D map, right? Two-dimensional matrix, right? Now you just do a random experiment, you do a Gaussian random matrix. How many times you would create a natural image out there? I don't think you'll get anything like by the time I die. Like you start the experiment by now, you never will see. I mean, even though someone say that one kid randomly type it will become a poem or something like that, but in this case, it's extremely unlikely. Lateral images are just very untypical in a sense. So therefore, you need to add some regularization here just to make sure the input looks like an image. And this is any kind of regularization. Just make sure this looks like an image. So if you do that, so this is some experiment here, like back in 2014. So it looked into, I think it's the, it's from the last layer, basically, from the last layer, and it just, I think it's an Alex Lab, something like that. So you have, this is the input image, you go into the last layer, you fix you record that as find not, and as I said, you just trying to optimize this, find the x such that you will have, this image will generate in the last layer close to find not, but also it looks like an image. And of course, this optimization problem is hard to solve. Typically, it's like, again, like by steepest descent. So therefore, like the result is kind of stochastic. So every time you play with this, like trying to optimize that, you get a little bit different result. So therefore, this here shows like 5 different results here. And so you can barely, I guess you can kind of see, okay, there's something here. So there's some information there. And of course, this is the last layer. Okay, what do you imagine if you go to the earlier layer? Do you expect like it to be, the image looks, if you go for the same process, then the resulting image will look more like the original or like less like the original? If you go back, this is we fixed the last layer. So we trying to optimize the input image to have basically match with the last layer of the original image. So now my question is like, if I try to match instead of the last layer, I match the coefficients in the earlier layers, then do you expect the resulting image will be will look nicer, or like will look more close to the original or less close to the original. Actually, if you guys are looking at the slides, apparently this is just okay. Anyway, so if I go to the earlier layer, so this is 1 layer before that, so it's a little bit better. I mean, if you go like way to the earlier layers, then it's actually you can imagine, because like you have lots of information, right? If you go down the layers, so therefore it's actually harder to get back to the original. So therefore, if you keep the earlier layers, kind of like trying to match the earlier layer, your image will be closer to the original. So so this is like I mean, here I'm trying to okay, what should I say? Okay, and anyway, let me. Okay, a slightly different setup will be like, instead of trying to get the something close to the original image, I want to do something very similar, basically, but in the earlier experiment, we kind of fixed the entire layer. So you can imagine that entire layer is fixed. I'm trying to optimize that. But let's say if we have a whole little letter here, and in the last layer we know that like one of the coefficient is corresponding to a man, and like one coefficient is corresponding to a boy, and one is corresponding to a dog or something like that. Now I want to see like what's a typical boy is like, or a typical mouse or is like, or something like that. So one thing I may do is like I instead of fixing the entire layer, I just fix one coefficient here that correspond to a dog, for example, and I go for basically the same thing. Then we will have like basically generate something like a typical dog or something. But it turns out it won't be that easy. But I want to show you is like the progress for this kind of stuff is horrible. Oh, I don't say horrible. It's like scary. I would say as a anyone like working in the university or trying to catch up, this is just really scary, because like what I'm showing you like each year, it's just like I'm sure that I need to change all these slides the next year. But anyway, so this is like the earlier results, like 2014. So you can kind of figure it out, like, okay, this is a cup here, but there's multiple cups here. There's lemon. I'm not sure you can see it. There's bell pepper. So basically you fix the class like here, like fix the class cup. I'm trying to generate image of cup. Of course, again, like this is class stochastic. Each time you generate a little bit different image. So this is a computer keyboard. I'm not sure you can see this, but anyway. So now. Then very much later on, like just 2015, people just figure out a little bit better regularization, then get a little bit better like images. Now it's like much more visible. Like you can kind of see, okay, this is actually a flamingo. I guess it's quite yeah, and I don't know this kind of stuff. This is still like it's better, but still like it's not easy to recognize. So this is a table, a billiard table here, and there's a teddy bear here. Okay, there's a chair here. Now I'm actually okay. This is of course the original image. So they fixed the class trying to generate the original image. And at the same time, like you fix the class, you can also like instead of generating the original image, you can also generate different layers of features, right? So and this is the result of different layer of features, and if you look at the lower layer, sometimes you can get even a high layer, you can get better visualization of, or like you can easily figure out what is that. Then the original image is when when you try to generate all the way the image in the first layer. I don't know. I guess I pretty mess up here. I guess you guys are lost. Is that? I feel like I didn't say it. So maybe I should repeat. Like this here is go through the step, generate the image, right? Generate one image. But you can combine this with the visualization method we described earlier. I'm using that. We can also visualize the later layers, right? So then you have stuff like that. So yeah, and we have different layers here. But then pretty quickly, I guess this is the work in 2016. Now it's getting even better now. It's just 1 year afterward. And you have something really much better. And the way they did it is like, if you think of a classes that, for example, you say a chair, because they have all kind of chair, right? So therefore, if trying to generate an image kind of representative to a chair class, then you will get a pretty messy images, pretty messy image. But what we can do is like, we can start with some random image, then we try to generate the class of chair. But because in the chair class, they have many mode, right? I would say like in the chair distribution, there's this kind of type of chair, you have this type of chair. Then you will look into like the current random image, which kind of chair is like it looks closest. Then you're trying to match to this kind of chair, basically. So that's basically the rough idea. Then doing that, they can do quite a bit better. But then the scary part is not yet. So this is a more result. Is pretty nice, strawberry orange. Then the scary part is this one. This one is like, I think it's work back in I don't have the date here. It's 2016 again or 2017. So they combine with some generative network. We didn't talk about that yet, so we'll talk about that probably like a couple lectures later on. And the generative network basically will generate an image. So they train now end to end. So here they try to basically you want to have the train the input here. Wait, what I'm doing? Okay. So what they do is like they train two ways. So one way is like they try to match one of the layer. I mean, that other way they're trying to train it like to map one of the class to kind of match one of the class, and the result it turns out is like just amazing. So this is the result. So and this is all kind of like simulated images basically, and you can just give in the class name there. You can simulate an image, and this just look pretty realistic or pretty artistic. This is a cell phone, and this is an aircraft carrier. It's pretty cool, yeah. And so probably there will be more. I need to change this slide next year, I think. I don't know what.
If you were to generate a new set of images, would they be different? But
yes.
It would still be jeans or TV or cell phone or aircraft carrier.
You mean that next time it generate the image, or like each time it will generate a different image?
Oh.
Yeah.
That's pretty cool.
Yeah, that's something like and of course like this whole thing you as you look at that, like apparently like those work as an artist immediately find all this very interesting, right? And then therefore like there's art like nowadays like just using neural network to build art. And the first I guess the first work is by Google, like they call it Deep Dream. That what they did is like the idea is pretty okay, there's a template code snippet here, just a tiny part of the code here. So so the key point is here. So what they did is when they do the backpop, they the original backpop is you have some gradient. What should I say? Okay, yeah. Let me start from beginning. So first you have a letter, right? Let's say you have Alex letter or something like you train the images. So you train the image letter. Now you have an image coming in. So you can compute the coefficient, right? You just compute all the coefficients. And then you can go into one particular layer. You say I'm going to dream in this particular layer. So what we did is what we are doing is we basically will reinforce like all the coefficient that's already big and then make it even bigger. So that's what we did here, right? So if we have some coefficient there's basically x here. So along that direction, I will set the gradient kind of proportional or just equal to that value there. So then in a sense, like when we pop back, we just make the feature correspond to that particular coefficient. If it's already at the beginning, it's kind of big, we will make it even more bigger and like more emphasized. And so the end result will be something. This one is not very clear, but we have bigger images. But it turns out because at the beginning, people all use like AlexNet and like GoogleNet and all these like the network are trained using kind of ImageNet and so on. And ImageNet in the data set just have many docs there. So therefore, it turns out like you will just, if you do experiment like this, they look at everything, it looks like doc, it will just reinforce that. So therefore, like have lots of funny things like dogfish, like camel bird. This is like official name like by the paper. They just like give them name. So anyway, and of course you can kind of boost in different layers. For example, like the earlier example, it boosts, I'm not sure which layer it did, or maybe the last layer. And then this one, like, it boosts like in different layers, then like it just have different results like in earlier layers. And you can, of course, if you want to do a high resolution image, it typically is pretty slow from scratch. But one thing people do is you can kind of downsample into a low resolution, and then try to generate one image first, like just not generate an image, but trying to backpop, trying to get it to converge first, and then you scale it up and redo it again multiple times. So then you just do a multi-resolution approach. Then this way you can do a even high resolution pretty efficiently. So for example, like you can do a 4K images. I guess like this is more images. Like this probably trained using a different data set. It's not ImageNet, but something else. Is I think this is a data set full of architectures from MIT. So therefore, like everything it just looks like architecture. So it just creates stuff like this. And so I don't know whether I should stop or maybe I'll just stop here. And any questions there from you guys? Yeah, actually, if you, in terms of project, like you guys can think of stuff like that also. And lots of source code are available. For example, like, and these things go really fast. For example, like I think like the instructor in Stanford, like one of the instructors, like Justin Johnson, like he has an implementation like in 2015 or something, and then he has couple works later on, but immediately there are lots of work from everywhere, and you can, but you can still pull out his original source code and you can play with that and make changes and. But of course, in terms of project, you cannot just download the code and play it and run it and that's it. So you need to do a little bit something.